So these are the four things that we're going to look at and that you need to be able to predict reactions for. The first thing is the formation of a solid. So you're going to need to know the solubility rules. The next slide kind of shows those. This is going to be the majority of our reactions. The second is formation of water, which is an acid and a base, otherwise known as neutralization, and that will be some of our reactions. The formation of a gas, we're going to look at just one where carbonic acid breaks down, and there will only be one of those in the test. And then lastly, we're going to look at transfer of electrons, and those are going to be called redox reactions, oxidation reduction. Now these right here are called partner switch or double displacement because charges don't change. But these right here are going to actually change charges. Here are the solubility rules. What you basically need to do is know is that soluble means aqueous. So if you see nitrate salts, they're soluble. Salts of group 1, sodium, potassium, and then all of group 1, and ammonium and hydrogen plus 1 are soluble, so they would be aqueous. They dissolve. Chlorides tend to be aqueous, but there are some exceptions. Those are the exceptions, and they are insoluble, so they'd be a solid. Most sulfates are soluble, so aqueous, but there are some exceptions, and those exceptions will not dissolve in water, so they'd be a precipitated solid. Most hydroxide compounds are not soluble, so for most hydroxides you're going to put a solid, but we have our group 1s and group 2s that we basically say, look, they're going to dissolve, so those are exceptions. They'd be aqueous. Sulfides, carbonates, chromates, and phosphates are not soluble, and there are a few others that are not soluble. This is not complete. Acetates, C2H3O2 negative 1. Acetates tend to be soluble, and there's some others that the biggest thing you need to know is that Rule 1 takes precedence. So if there's ever a question, like let's say you had a sodium carbonate, and you're like, well, wait, sodium says it's soluble, the carbonate says it's not soluble, it'll be a solid. So which one do I choose? You always go with the higher rule. So if it would be sodium carbonate, it would be aqueous. Okay, so you have to visualize this happening. In one beaker, you have potassium and you have a chromate. In another beaker, you have barium and you have nitrates, and they are aqueous. And the reason I know they're aqueous, I look at Rule 1 or Rule 2, and it will tell you that these things are aqueous. They're going to break apart into electrolytes, meaning they're going to break apart, they're going to light up the light bulb, they dissolve. Now, we're going to pour them together, and a precipitate occurs. Now, how do we know a precipitate occurs, and what could it be? Well, it can't be K plus 1 and barium plus 2, because they're both positives. In the same sense, it can't be chromate and nitrate, because they're both negatives. You have to have a positive and negative coming together to make a zero net charge. So could it be potassium nitrate? Well, possibly. Could it be barium and chromate? That's our other possibility. Those are our only possibilities. So we check our solubility rules, and we see that Rule 1, Rule 2 tells us that potassium and nitrate will not. However, if you look down at the bottom, I think that's in the rules, chromate is a precipitate, and chromate is going to get together with barium and form a solid, dissolve. So how do we look at that? Well, I should have done that on the other slide, but what you would do is you'd say potassium nitrate, and you'd put an AQ there, and barium potassium chromate. So, try that again. Okay, so what we have is, let's do that up here. We're going to have potassium chromate plus barium nitrate. And what's going to happen is that potassium and the nitrate have a possibility of coming together, but we know they won't. It's aqueous. Plus, the barium and the chromate are going to come together, but they will be a precipitate. They will be a solid. So that would be the reaction. You'd write an AQ there and there too. There and there. Now, notice when the K gets together with the NO3, it's a +1, -1. Rookie mistake is to take those 2's and put them over there, like K2, NO3, 2. I'll say that occasionally. Don't do that. It's with a new partner. It's a +1, -1, 0 net charge, good to go. The story here is barium chromate. Okay, so if we had potassium hydroxide, we'd have potassium and hydroxide. That would be AQ. And we have iron, which is a +3, and nitrate with a -1, and that's aqueous. Now, they're going to switch partners, and K is going to go with NO3. Now, notice when it does this, K is a +1, NO3 is a -1. Don't bring that 3 over. That 3 was there because it was with iron. And look at our rule 1 and 2 with aqueous. Now, we're going to have iron with a +3 getting together with a hydroxide -1. Make sure you write that correctly. And if you look at the rules, hydroxide salts tend to be insoluble. So this will be our precipitate. That's the driving force for the reaction. Okay, so one other, I'd have sodium sulfate, +1, -2. I'd have lead 2 nitrate, and they're both aqueous. And then they're going to switch partners, and sodium is going to go with nitrate, +1, -1. Don't bring those 2's over. And Pb with a +2 is going to get together with sulfate -2. And if you look at the solubility rules again, you'll see that sulfates tend to be aqueous, except for a few, and this is an exception, which will become a solid. So this is a well-written equation on the balance and I'll be putting a 2 there. Alright, for net ionics, you need to visualize, ask yourself which ones are soluble and free, and which ones are not soluble and not free. Free ions are written with their charges. Ions that are not free are written in their compound with no charges, and we eliminate the spectator ion. So, potassium chromate, the potassium actually doesn't do a darn thing, because it's in the chromate. Potassium is then going to go with nitrate after the reaction occurs. So we know basically that this is, why does that not work constantly? We know that that's not going to be, it's going to be a spectator. It's not going to happen. The real story here is that barium, which was a free ion, and chromate, which is -2, they're the ones that actually did something. So that's our not ionic equation. We don't write the potassium, we don't write the nitrate, because they were aqueous before, they're aqueous after, they never did anything. This is our net ionic equation. Same thing here, I've got potassium hydroxide, and I have iron 3 nitrate. And what's actually going to, that should be a 3. What's actually going to happen here? Well, the K and the NO3 are going to get together, but they don't really do anything. They're aqueous before, they're aqueous after, nothing happens. What really is the big story here is iron and hydroxide. So what I'm going to do is not write this whole thing out. I'm going to actually just focus on the iron nitrate. And so I'm going to say Fe with a +3 and 3 hydroxides with a -1 get together to make FeOH3. Okay, and this one you could probably rate these without even, with checking your solubility rules, without even writing out the whole equation, because you know that sodium and nitrate before and after are going to be those are the not ionic. Alright, formation of water, otherwise called an acid-base neutralization. You're always going to have an acid which starts with an H something and then a base which is something OH. So this will always be the cation and this will be the anion. Strong acids completely break apart into water. Strong bases completely break up into water. Acids will do an H and something, bases will do something and an OH. The products are always water. So we're going to take hydrochloric acid, aqueous, sodium hydroxide, aqueous. They're going to do a partner switch. H is going to go with OH and Na is going to go with Cl. and we're going to get HOH, which is liquid water, and this will be aqueous. Now, it's not a precipitate, but it's certainly something that happens. And then, of course, H2SO4 plus KOH. We'll make HOH. Now, please don't write H2OH just because there was a 2 there. Don't do that. It's water, and then it's going to be K2SO4. I don't know if I can get that in there. Let's balance the equation. The not ionic for an acid is always going to be this, because that is what happens. The others are spectator ions. The chloride, the sodium, those are all going to be aqueous before and after. So this is the net ionic for neutralization, always. The one we're going to look at for gas is going to be very specific. It's going to be when they do a partner switch. Hydrogen is going to go with carbonate and sodium is going to go with chloride. Again, don't bring that 2 over. It's with its new partner. Now this is what happens, but immediately you say, okay, well that's aqueous, but that's aqueous too, so no reaction, that's what you should write? Nope. What you're going to do is you're going to take this. This immediately is going to break into, and I'm running out of room here, so I'm going to erase. But once you write that, once you write the H2CO3, what you should do is immediately right beneath it, write this. So let's say that you've written out H2CO3, and the reason you've done that is because hydrogen, like that. This is immediately going to break into liquid water and carbon dioxide gas. And that's all you have to remember, that one reaction. But you have to remember when you see that to write this and this.